Number of electrons to be filled in various orbitals is restricted by this Pauli exclusion principle. This principle, first given by the Austrian scientist Wolfgang Pauli in the year 1926. That means the number of electrons, how it will be accommodated in the atomic orbitals. There also one criteria is there, which is the Pauli exclusion principle. According to this principle, no two electrons in an atom can have the same set of 4 quantum numbers. That means every electron will have unique 4 quantum numbers. That means only 2 electrons may exist in the same orbital, and these electrons must have opposite means. What does it mean? We know that 4 set of quantum numbers means the principal quantum number N, azimuthal quantum number L, magnetic quantum number ML, and in addition spin quantum number. In an same orbital, the 2 electrons, it have the same value of 3 quantum numbers N, L, ML. But according to this principle, 4 quantum numbers should not be the same for these 2 electrons. And in this case, the spin quantum number is different. We know the spin quantum number MS, it has only plus half and minus half value. Only 2 possibilities there. That means plus half and minus half, these are in opposite spin. And this is called the opposite spin quantum number. So in the same orbitals, only possibility of entering of 2 electrons is there, and these 2 electrons, they have the same N, L and ML values, but these 2 electrons should have the opposite spin quantum number. That means if one electron has the spin quantum number value is plus half, then another should have minus half spin quantum number. This restriction imposed by the Pauli exclusion principle on the number of electrons in an orbitals helps in calculating the capacity of the electron to be present in any sharp shell. That means how to fill up the atomic orbitals by electrons systematically. Then Pauli exclusion principle also one of the major criteria which will help the calculating the capacity of electrons in different atomic orbitals. For example, subshell 1s, it comprises 1 orbital only. We know from the previous class I explained that s orbitals, and thus the maximum number of electrons present in 1s shell, how much? It should be 2. And in p subshell, how much? Because p subshell has 3 orbitals, px, py, pz. So each one will have the 2 electrons maximum capacity. So total, if we count for the p subshell, then maximum number of the electrons can be 6. That means 2 multiplied by the 3 types of p orbitals, px, py, pz. So total maximum number will be 6 for the p subshell. And similarly for the d subshell, we know from our previous class it has the 5 orbitals, and these 5 orbitals for this case, each orbital maximum capacity is 2 electrons. So for 5 orbitals in d subshell, the maximum capacity will be 2 multiplied by 5 is equal to 10, and so on. So how do we sum up this all about the Pauli exclusion principle? That the maximum number of electrons in the shell with principal quantum number n, if the principal quantum number n, then the maximum number of electrons in the shell will be 2n square. That means if principal quantum number is 1, in that case the total number will be 2 multiplied by 1 to the power 2. That means ultimately 2. And we know the first shell only have one subshell 1s and maximum capacity is 2. So this example is matching with this general number 2n square, where the n is the principal quantum number. And if you go for the principal quantum number 2, in that case, the maximum number of electrons present in that shell will be 2n square. That means 2 multiplied by 2 square. Ultimately, it will be 8. How? Because the principal quantum number 2, that means in that case the shell has 2s orbitals and 3 numbers of orbitals in 2p. So that means total number of orbitals 4, 1 for the 2s and 3 numbers for the 2p subshell. So in that case 4 and multiplied by the 2 electrons, the maximum capacity of each orbital. So ultimately it will be 8, and it is matching with this general equation 2n square, where n is equal to principal quantum number.